And now we go to the final presentation. Again, this one is sadly pre-recorded, and this one is by NAG, Applied Materials. I think this was recorded maybe a couple of days ago. And he will be telling us about manufacturing scalability of micro-LED displays using UV-pumped, cadmium-free quantum dots. Just for your information, this presentation is roughly about 20 minutes, in case you need to plan your trip.
Hi, my name is Patibandla from Applied Materials, and I apologize for being absent from the forum and thank the organizers for accommodating my presentation to you all. In this presentation, I will discuss manufacturing scalability of micro-LED displays using UV-pumped cadmium-free quantum dots. Our team at Applied made tremendous progress on this approach, and we are currently setting up a pilot manufacturing line at a partner site with a capacity of 1,000 smartwatch display modules per week. Let's jump right forward. Let me start by talking about Applied Materials. We are a large semiconductor and display manufacturing equipment company with nearly $27 billion in revenue and 34,000 employees globally and in 24 countries. And we spend over $3 billion in R&D and closing in pretty close to 20,000 patents. Here are a couple of pictures of our semi and display tools. They are large, they are highly engineered tools to enable atomic scale engineering at nanoscale device fabrication at an industrial scale. Displays are ubiquitous. We have recently seen the industry transition from LCD to OLED. So why another transition? The reason there are a couple of new and demanding applications that are emerging in the display industry. One such is AR/VR, or what we call near-eye displays. These displays are very demanding with respect to brightness, resolution, energy efficiency, and auto displays are expected to go through a revolution as autonomous driving becomes a reality. The auto displays will demand high brightness, transparent and curved form factors, and extended use temperatures. There's also a need to enhance user experience of mobile and handheld devices. Higher brightness in the outdoor use, longer battery life, low blue light leakage, and foldable screens are the most desired features. There is also a value proposition in luxury TV market for a more immersive experience. In fact, many of the micro-LED displays showcased in CES are typically large, hundreds of inches in size, like Samsung Wall and Sony Crystal LED display. High viewing angles and in-your-face color contrast are the key attributes. So displays, as they become more and more ubiquitous, more and more demanding with respect to performance, micro-LEDs play a critical role in enabling that. What is a micro-LED? Before getting too deep into our approach on how we use micro-LEDs in making our displays, let's think about what LEDs are. LEDs, gallium nitride LEDs, have been around for a long time. They are used in general lighting and backlighting units in public displays and TVs. In these applications, they are as large as a millimeter down to hundreds of microns. Micro-LEDs, on the other hand, where each one of these pumps a subpixel, are tiny. They're preferably tens of microns on a side, and even maybe as small as a single-digit micron in size. They are required to be mass transferred from their growth substrate to the display backplanes. The micro-LEDs are great in many ways, but they do suffer some engineering challenges. One of the key areas that they suffer from are they have multiple interdependencies: the size, cost, external quantum efficiency, color gamut, such as full width at half max of the emission peak, as well as the peak wavelength. They do shift and they have dependencies on each other. In order to make the micro-LEDs reasonable in price, low cost, we need to make them small. However, when the size is reduced, the EQE also is reduced. And therefore, we have to think about how do you improve the EQE of the micro LED dies as reduce